warm welcome to the Friday finalist presentations at the Monaco Energy Boat Challenge 2026. This session will feature the finalist presentations for the Design Prize and the Eco-Conception Prize. We will begin with the Eco-Conception Prize, alternating with the Design Prize. Firstly, the Eco-Conception Prize recognizes projects that place sustainability and environmental responsibility at the heart of their research and development. The teams have assessed the environmental impact of their vessels throughout the life cycle, from conception and production through to end of life. Before we begin, it is my pleasure to welcome Lizzie Howard, Project Manager at Marine Futures, to say a few words about the Eco-Conception Prize. Thank you.
Firstly, thank you so much to everybody that is here today, everybody that submitted your reports and your submissions for the prize. It was a really amazing quality of assessments, and there were some great innovations and insights from all of the teams. We're really pleased with those that we've been able to shortlist, and we're looking forward to seeing your presentations today. The aim of this Eco-Conception Prize is to highlight and reward the creation and development of genuine impact reductions. So whether that be reducing CO2 emissions, looking at noise reduction, looking at reducing waste, improving efficiency throughout the life cycle. But we're not just looking for solutions that look good on paper. We're looking to see how are those solutions stack up in terms of feasibility, performance. How are you managing and handling those trade-offs to produce something that is not only lower impact, but is also something that can translate into real industry change. So the Monaco Energy Boat Challenge is a platform where designers and engineers can try, fail, learn, iterate in a way that you can't always do in the industry. So we're really excited to see the low impact decisions and low impact solutions that you've come up with. We're looking forward to seeing some of those today. So yeah, thank you, and well done to those of you that made it this far.
Thank you very much, Lizzie, for the meaningful introduction of the Eco-Conception Prize. So as we are alternating the presentations, I will continue with the Design Prize, which recognizes the outstanding boat design that combines engineering excellence with aesthetic brilliance. And to introduce this part of the session, I would love to welcome Gilles Vernet, Head of Design at Ocean Co, to say a few words. Thank you.
So again, thank you all. This year we have plenty of part entrants for the Design Prize, and I think that's your involvement in this prize, which is quite far from your regular duty as engineers, is a sign that you're having the understanding of what design could bring to your product and to your project. There is one message that I would like to say to you, is that we had, unfortunately, to make the choice of the finalists based on some criteria which are linked to the aim of the Design Prize of making your product or your project as one single element, from the cockpit to the seat and everything which is linked to the human. So the aesthetic, but also the use of your boat. Basically every technical part and are really linked to the innovation and some other prizes. Our aim in the Design Prize is definitely to get you understanding your project as one single object, and applying the design philosophy and design process on your project would be to give to your entire prototype a meaning, from the interior to the exterior, from the user to the people, the public looking at your boat. So there should be this aim for you to focus not on a single part of your boat, but to think your project as a whole, one single project. And with this in mind, you will improve year by year. It's quite still a new price in the competition, and we see improvement every year, and we will still explain the aim of this price to you, so you also will improve. But thank you very much for all the entrants and the fact that you are more and more attached to bring your project to the design price. That's all. Thank you.
Thank you, Gilles. It is very inspiring to hear from such an important voice in the world of design, especially for the yachting industry. And next, to welcome a company, it's Cshaki presenting from YH2O to explain a bit. It's not quite part of the Tech Talk presentations, but to explain a bit about their innovations and design and from the Chinese market and the Asian market. Thank you.
Thank you very much, Carol, and thanks everyone for listening. We are YH2O, and we are the first Chinese team for fuel manufactured in China, and we participate for C-Lab. For the day one, we win like the fourth in maneuverability and the third for speed record. And currently we are ongoing with the 16 naval method. So just start. So we are aiming to creating the future electronics and intelligence to move forward for water mobility. Our mission is to, we are the first civilian fossil hydrofuel boats made in China and Asia, and we want to look forward for zero emission and intelligentality. So currently, the model you have seen, probably you have seen our racing, and this model, we currently implement with a passive falling system, which can save up to 80% of energy savings and 70% improvement in stability. And by our calculation from environmental and economic point of view, we can reduce consumption by 75% and expenses for energy cost around 94%. And this is our pipeline. So before launching this project, we have more than 10 years of yacht design. Our designer is graduates from Polytechnic Milano and worked 2 years for Fidelity. So this whole concept, starting from a sketch by August, like closely 2 years ago, and we scale up and complete the EVT version and doing prototyping by last May 2025, and we rent a production line and building up our first MP version. So this boat is actually the prototyping for this version, and currently this seat is, we contain 3 seats, and the other seats contain 5, already done the EVT version, and we are working on the active, adaptive falling systems. So this is the prototype, and which you already seen that also tomorrow by 2 p.m. after the events, you can experience that. We have an open slot for that. And the longevity is less than 5 meters with durability of maximum cruising knots from 18 to 33 and capability up to 6 hours. And this was Eric Schmidt, the former Google CEO. He's our angel user, and this is some marketing that we are. So finally, compared to so firstly, we have 3 tech pillars. First one is the hydrofoil. Inspired by aircraft, we implement the active flaps in our foiling systems, and we can improve maneuverability and without compromising any drag reductions. Second pillar is a brand new port motor that we will implement in the next generations to be equipped with a power driving trim. Thirdly is the smart cockpit systems. We want to active the stability and with evidently more stronger resistance. And we all know that like electronic is zero noisy, and in total, this is an AI autonomous driving system. This is a video. Can we like start it or? Is this a video can be placed or? Yeah, please. And we can move to the 13 seconds. Okay, so what I want to show is a gaming system that we implement. So within the gaming system, we can do modification and estimation to the real scenarios. So let's move on. So in total for technical aspects. So with energy savings less than 50%, 80% less drags, and silence to 52 dB. And this is our future plan. Currently, we are doing CE. For the next year, you're gonna see our like EVT version with 5/6 flagship again in the game next year's, and probably this you won't able to see this. Also, we have some algorithm and key indicators for water resistance with the foiling and without the foiling. So you can search the website fly/h2o.cn to see more like indicators. And probably this note. So we want to present our whole team. We are a team of less than 20 people. And we used to build larger ships with maximum like 124 meters. Wedding boat in Vietnam. We also present. We have designed a ship in Italy. And thank you so much for offering this opportunity. And looking forward to see you guys via this social media and stuff. Thank you so much. Hope you enjoy your days.
Thank you very much, Sasha, for your presentation. I would now like to announce to the stage our first design prize from physicists Monaco Energy Boat team. Thank you.
Hi everyone, I'm Milena, and together with Gabriele we're going to present our new racing cockpit and the process that guided us to the realization, from the design phases to the engineering part. So it started with the new 750 millimeter regulation that gave us the question if adapting the previous chassis was the best idea, or if we can, and if it was the best idea, or carrying its limitation forward, or try to start with a new project. Because with the previous chassis we have multiple separate elements, more weight and less ergonomic, and we decided to try this new solution. So this led us to the question, how can we transform the cockpit into a fully integrated system, optimized for performance, ergonomics, and future adaptability? And we started analyzing our previous chassis and its limitation. As we can see, the previous one had the restricted driver arms movement and the compromised dashboard visibility for the steering wheel. So
on the mechanical side, we can see that, you can hear me? Yes? Okay. On the mechanical point of view, we can see that all the structure rely on two longitudinal beams, as we can see, that brings all the parts of the boat, like for example the cockpit, the cooling system, the battery box, and the motor mount. This was a problem for us because it means that we have a lot of screw to fast before going in the water, and it's also really difficult to keep the right maintenance on all the pieces. And for this reason, we said, how we can solve all these problems with just one solution. So rather than solve all these problems, rather than solving all these problems one by one, we try to find out a solution that can solve all these problems with just one shot. And our answer is a self-supporting structural monocoque. So a really big one structure that brings all the load and integrates the battery system, the pilot space, and the motor mount. What I want to say is that all the surface that we have inside of this cockpit has a multiple purpose, for example. Like, for example, it's not just maybe structural part, it's maybe also a surface that has to be ergonomic for the pilot, and at the same time it has to be hydrodynamic or hydrodynamic. We started, after that we decided and fixed the philosophy at the base of the project, we started to fix other design constraints. Like, for example, we started at the beginning with the driver dimension. So we take a lot of measures of the pilot while he's moving inside of the cockpit, while he get in and get out, so while he's driving and so steering, and we bring it on a paper. And so at the beginning we designed the cockpit of the pilot. The second one was the regulation limits. For example, the 700 millimeters between the clamps that we have to keep it free, as said by the rules of the Monaco Energy Boat Challenge. And moreover, there is also the rules about 500 millimeters between the pilot and the battery. So the third constraint was try to move the battery in different configurations. So we found out different configuration, like in a longitudinal way, transversal wave for the battery. Why this? Because we want that this cockpit, we want that it will be useful also for the next development of the boat and for the next development of for the energy system, maybe battery, maybe hydrogen. So we want to keep it usable also for the next generations. And at the end, we worked also on the motor integration, so about the motor mount, the right angle of the transom, and also the right position of the motor to be sure that the height of the motor is right.
So after this analysis, we try to comprehend all these things in a design language that was current, and we find that futurism was the best thing representing all of our ideas, because it represents the speed, the force, and we try to analyze it in that way. And also we inspired our project in the high performance racing boats and its curves, and we try to give this language also to our boat and our project. As we can see, the result is a big unique form that follows the shapes of the force and the speed and all the things that belong to the future. And to do this, we designed it around the driver. As we can see, we did lots of calculations in the measurements of the envelopes of the pilot and also of the components inside the boats. And we tried also to design the seat to be more comfortable for him to drive it, and also the steering wheel that is inspired from the Formula One type to give more visibility to the dashboard and also to be more comfortable to drive it. As we can see here, we reported some of the measurements we took of the pilot, the angles of its legs that reminds of the sitting in the Formula One also. As we can see, the beam is under its knees, and also the increased visibility of the dashboard that is integrated inside the cockpit. And yeah, here we can see also the dashboard project, because we did a new UI for it that is context dependent, because it has different interfaces for different races. For example, during the speed race, it shows parameters like speed that are bigger, and for the endurance one, maybe it shows other parameters that are better for the pilot to see it.
Okay, as we can see, for the new cockpit, we decided to integrate a big cover, because the previous solution, we had just small openings, so it was difficult to work inside of the boat, to load the battery inside of the battery box. With this solution, as we can see, we have a big cover that when we open, all the guys can work inside of the boat, and it's also easier to keep it like waterproof. Also, we redimensionated also the solar panels to let it free an access for the pilot to get in and get out. We focused also on lowering the center of mass of the boat, because it helps a lot to keep the setup right when we go in the waves. We reduce pitch and roll. To do that, as we can see, the pilot, thanks to this solution with the monocoque, we can see that the pilot is seated in a really low position. And this solution naturally provides a support for the leg. So we have increased a lot the ergonomics of the boat. And the driving position is like a Formula One style driving position. And then we integrated also the motor mount for the motor to have the right angle and the right aids. About composite layup and something like that, we haven't worked only on composite layup. We also decided to work a lot on the geometries, on the cross-section, of the geometry of the cross-section. For example, as we can see from the first scratch, we worked a lot on curves and lines. We integrated a lot of convex and concave lines to increase the stiffness of the cross-section of the boat. And as we can see from the FEMs that we have done, what we have done is right. So we increase the stiffness of the boat, not just with carbon fiber, but also with the geometry. So without increases weights. The manufacturing part of the boat, as you can understand, is the biggest part and most difficult one, because at the beginning we wanted to 3D printed it with a pellet, but the company had the problem, so we started to build it in a really old way. So with wood. So we started from the sheet panel, we cut in 2D, we started to put some ribs, we cut other panels that we had to bend to follow all the geometries, and then with a lot of screw, a lot of resin, a lot of putty and sanding, we reached to have a good mold and prepare it for the infusion. So this is the result, the PB526, the boat that we have bring this year on this harbor. We worked a lot on the materials. For the structural part, we decided to use a high-performance carbon fiber. But where the parts were not like structural, we decided that the sustainability was the key. For example, in the inner part of the boat, on the walls, there are the power ribs. Maybe you know it. It's like a net made in flax fiber that increases the stiffness of the boat. We increased also the leader and for the seat. And finish. Sorry.
Hello. Thank you very much for your presentation. I apologize for the bell. I would now like to open up the floor for the jury's questions.
It will be Gilles today.
I would say that you could have like final word, but thank you very much for your very extensive presentation. I think that we never had such presentation so far from your past experience, which is also good for the other teams to be shared, problem that you have faced, the logic behind your thinking, and also the future proofing of future development. So that's very, very good. Question about the way it's technical more than design, but it's part of the design process, engineering. You made the mold, integrating the passage of the beams.
Yes.
I mean,
yes.
basically, that was integrated in your monocoque
Exactly.
design, meaning that you could not, let's say, slide the monocoque on the beams, so that you have anticipated some system inside to manage the longitudinal center of gravity position.
Yes, this is a really good question. Thank you so much. Because about the longitudinal position of the boat, we worked a lot because having the right setup is really important to reach high speed, but also the right efficiency on the endurance race. Since we have the 3,000 millimeters fixed from the cockpit, we decided to integrate on the battery box, as we can call it, two longitudinal small guides on which the battery can slide. In this way, we can find out the right setup for the battery that influences a lot the position and the setup of the boat. So we work on that, and the pilot can also move a bit, like between 15 and 20 centimeters away on the back. Thank you so much.
Sorry, I've got another question from the jury here. Thank you very much for this beautiful presentation. I have a question regarding the ergonomics on the pilot. You did work quite a lot on this, so my question is very simple. Did you base all your measurements on a standard ergonom, or did you base your measurements on the real pilot?
We take the measures on the real pilot, so to design the seat, but also the cockpit on himself. So it was like more comfortable on him. Yes.
And how about if you were in the need to change pilot?
I'm really similar to him. So
right, okay. There was always a plan B then.
Yes, I'm the plan B.
All right. Thank you very much.
Okay, thank you so much for your presentation. I'm curious, other than the materials, are there other sustainable means that you integrated? Any other research directions? Any other aspects of sustainability?
Yes. As I was explaining, we worked a lot together between design and engineers because they helped a lot to have a really beautiful boat, but also that works really well. About materials, we have also recycled 3D printed parts to, for example, these ones that are the ones that brings all the load of the boat are made in a particular filaments that we developed together with a company. So we make custom filaments to realize these parts. So this part is recycled 3D printed materials, really stiff, really strong, but also we work a lot, as said before, on composites. So we had some part in flax fiber, some flax in basalt fiber, and also the carbon fiber. We take a lot of in consideration the pattern of the carbon fiber that we use. For example, it's not easy to see, but for the cover we have a twill wave pattern because we want to reproduce what there is inside. I know that you cannot see it, but so I invite you to come to our box in the paddock to see it. But inside we have ribs inside, so we want to emulate what there is inside. If we look at the bottom part, we have a plain wave. Why? Because inside we have the power ribs. That is a net, that's a geometry that is like square. And so we try to work together as engineer and as designer also in this way.
Thank you very much.
Thank you very much. Thank you. Next, I would welcome to the stage our first Eco-Conception Prize presentation from FEUP Academic Solar Team. Thank you.
Hello everyone, my name is Francisca and this is my colleague Simão. And we are here to represent FAST, FEUP Academic Solar Team. FAST was born to fill a gap in the naval engineering at the University of Porto. And our goal is to build a vessel where technology powers sustainability. Thus, our core values are sustainability and reduce the environmental impact. We achieve this with an 100% hull made of flax fiber, which transforms CO2 and utilizes renewable energy. Furthermore, our low emission production process proves that ecological solutions are viable for both competition and industry.
Now, to briefly describe our prototype that we brought here this year, Atlantico is a 6 meter by 2.4 catamaran with 3 T-shaped hydrofoils that weighs around 300 kilograms. It has a battery of 1.5 kilowatt hour that, together with the solar panels, permits our vessel to cruise for around 1 hour. It also has a brushless motor that can peak powers an output of 10 kilowatts, making it able to reach a top speed of 20 knots. On our development plan, the team was founded in late 2023, and that's where the development started. In mid-2024, we started the manufacturing of some of the main parts of the vessel, and last year we presented this prototype. It has been testing and upgraded since then. And this year we adapted to compete in the AI class here in Monaco this week. It will be competing until the end of the year, and we expect an end of life in 2027. Now moving forward to our 2 hulls. This is one of the main questions that kept us thinking. How could a hull be more sustainable? And we being a hull, one of the main parts of a vessel that is commonly made from materials that are not as sustainable, like carbon fiber or glass fiber, and being produced with manufacturing processes that are not also environmentally friendly. We try to answer this question with 2 main points. Being the first one, the hull design. And in the hull design, we opted for the 2 identical hulls. In order to only need to design and manufacture 1 mold for both hulls. And with this, we could mitigate some of the environmental damage from the manufacturing stage, and also enhance modularity and simplicity. The second point of our answer to this question would be the material choice. We opted for the usage of flax fiber for the hulls, and also cork as a core for the sandwich structures of the bulkheads. These are both natural-based materials with great mechanical performance when well applied, and also additionally, Portugal is a big cork producer. So in that way, we're also taking off the environmental costs of the transportation of the material. And here we have two bar charts of the comparison between a carbon fiber and a flax fiber hull, but in terms of energy consumption and also the emission of gases. Now, another part where we applied, another part of our prototype where we applied the eco-conception approach was the hydrofoil system. And we divided this in three hypotheses, being the first one, the first hypothesis, the monolithic aluminium CNC machined hydrofoil. This one is the fastest and the most straightforward method. It is highly reliable, and the aluminium has predictable and isotropic properties. But it has a big drawback. We would need it. It would have a high energy consumption and high material waste due to the fact that we only machine one hydrofoil by each time. The second hypothesis would be, then we moved for the second hypothesis, which was a forced carbon fiber hydrofoil with aluminium molds. With this, we would have almost near zero material waste in the forced carbon, but there's a big drawback in this one. We would need to manufacture a high quantity of hydrofoils to mitigate the carbon footprints of machining the aluminium molds. And then we moved for the third hypothesis. This was the final and the final hypothesis, the one that we chose. It is the forced carbon fiber hydrofoil as well, but with pine wood molds. With this, we were able to keep the idea of using repurposed chopped carbon fiber, but then combine it with a pine wood mold, which is a sustainable and natural-based material. With this, we could solve the tooling paradox that I talked before about the aluminium molds, and also it requires less energy to machine the wood for the mold, and it's also a cheaper material. After testing, we did find some drawbacks in this option. The pine wood is susceptible to warping due to heat and moisture, and also requires an extensive surface preparation. But in the prototyping point of view, it was verified. We verified it that it's the best option, since we were able to produce the 5 hydrofoils that we meant to produce, and the mold is still intact and ready to produce more. And here we have another bar chart in terms of with the comparison of the three methods that I talked before. We can see that obviously the forged carbon with pine mold is the best one, and that's the forged carbon with aluminium molds in this case, just because we would need to machine many parts for the mold. It would be the most harmful one.
Moving on to our energy storage. Initially, our battery was composed of LTO cells, lithium titanium oxide. I'm sorry. They weighed 21 kilograms and have long durability, a fact that immediately caught our attention from a sustainability point of view. However, from an engineering perspective, it revealed a flaw. The production of these cells carries a massive carbon footprint, 206 kilograms. Usually, this initial high environmental cost is offset over time by the battery's lifelong span. So this led us to evaluate, but for a racing prototype, just like this, just used for testing and for short competitions, we will never come close to reaching the end of that life cycle. This led us to evaluate NMC cells, nickel, manganese, cobalt. The production of their carbon footprint production is only 104 kilograms. Plus, their superior energy density allows us to match the exact same performance while dropping the battery's weight to just 7 kilograms. So, therefore, we moved forward with the NMC battery, successfully aligning our environmental responsibilities with our performance goals. We designed Atlantic so that every major component can be easily disassembled and transitioned into a high-value second life. Firstly, the hulls. They were designed to be convertible into kayaks. We simply trimmed the top to a standard height, adapt the deck, and seal the strut cavity. As for the flax fibers we cut off, they won't be wasted, and we will reuse them for reinforcements of other future vessels. Secondly, the crossbeams. Since they will still remain structureless sound, we will give them to the University of Porto's rocketry team. And finally, we select the sensors and the electronics, the most versatile ones so that we can transition to other vessels. Here we have the life cycle assessment results, which are critical for us to understand what we could do better. As you can see in this global warming fossil chart, our bigger impacts come from 3 areas: the hull mold, the machine aluminum parts, and transportation. It is important to note that the hull mold's footprint is only this high because Atlantic is a single prototype. This impact will be mitigated by a higher volume production. These results. Thank you for your attention.
Thank you very much for your presentation. I will now again open the floor to the jury for their questions. Thank you, Lizzie.
Thank you so much for your presentation. I think there are lots of highlights in that I think were really great to see. The fact that you're considering the duty cycle of your prototype and how it's going to be used in all of your calculations is really important to see. You've got a lot of things on here that lots of small iterations and changes you've made to your design to try and make it lower impact. My question to you guys is, of all of those design decisions that you've made at different materials, what would you recommend to industry? And what were the challenges that they might face in adopting that solution? So which of the ones that you've had would you say, this is what I'd like to put forward to industry?
Okay, so maybe one of them would be the flax fiber usage on the hull. There's always drawbacks when we're talking about this type of decisions. When we talk about the flax fiber, it has lower stiffness than carbon fiber or glass fiber. It is harder to work with and harder to make it perfect on the hull. But it would be a great option to use. Also the hydrofoil would be the hydrofoil. No, sorry, the forced carbon that we used on the hydrofoil. It's a great decision as well. Even though it has a lower stiffness than the laminated carbon. I think it's a great option.
Did you find with both of those, did you find that the performance difference, have you felt the performance difference? So obviously there's lower stiffness in flax, for example, or in this forced fiber. Did you actually notice a change in the performance of your vessel because of that?
Our vessel is actually quite heavy because of the usage of flax fiber. Even though that we tried to make reinforcements, local reinforcements, instead of making the whole hull with many plies. If we used a more performance directed fiber, maybe we could have make a less heavy boat, and the performance would be increased as well, of course.
And when you were measuring all of this, were you weighing up the difference between, okay, if it's heavier, it's going to have higher energy use, versus if it's lighter? How did you find that trade-off? How did you find that balance when you were working it out?
The balance between?
Between the amount of energy that you're going to be consuming if you've got a heavier vessel versus if you used a more performance material. Maybe you get a lighter vessel, you can use less energy. So did you look at the sort of balance between impact there?
that's actually a question that we would need to further analysis. To do further analysis on that, of course, when we use a fiber that is stiffer or with better performance, it would be lighter, but and the energy consumption would be lighter, but
however, we just try to minimize all the weight as possible as we can. So, for example, the battery, we save like 18 kilograms. We changed for the new battery with the NMC cells because of their energy density. So, less weight, less energy consumption, as you said.
Thank you very much. Would we have one last question?
I'm just curious what resin you decided to use during the lamination, and why did you choose it?
Yeah, that's actually a great question. Thank you. The resin that we chose actually still it's also a bio resin. We use the bio resin that has near 35% of carbon that is from a bio source, and that's another option that we took to minimize the carbon footprint of our hull and our boat, our vessel. Thank you.
Thank you very much. I'm happy to now welcome to the stage Adria Racing Team with their design prize presentation. Thank you.
Hello, everybody. My name is Lara, and this is my colleague Rocco, and we're from the Adria Racing Team. So, we're going to talk about our design, but before we talk about our design, we wanted to tell you more about us. So, our team is called the Adria Racing Team, but we're all a part of the Association of Applied Technical Sciences from Croatia. It's located in Rijeka, and our association was founded in 2018. So our team was established on innovation, sustainable engineering, and teamwork of many young students from the Maritime College and from Rijeka's Engineering College, or RITEC, as our Croats know. And we just wanted to take a moment to say that the Monaco Energy Boat Challenge has allowed us to transform our learning into competition, and the competition into a great experience that is of great value to us and our association. So let me give you a bit about our project framing and a little bit about our context background. So our project was designed on an electric racing boat, a cockpit that balances lightweight construction and system integration. It was inspired by Rijeka's motorsport culture and also by Rijeka's engineering background or heritage, especially by our torpedo, which is an underwater missile, as you know. So the design challenge was simplifying the complexity into a single efficient system without kind of compromising the performance of our vessel, which is Wilson. So it leads us to the question, how can we design a structure that integrates all key systems while remaining lightweight, safe, and aerodynamic? So there are many different kind of ideas and things that we kind of searched for, which is system integration, safety standards for our vessel, and high stiffness at very low weight with minimal material usage. So Through research and analysis, the primary constraint for our vessel was weight and mass, because the bigger the weight and the bigger the mass, the lesser the speed, acceleration, efficiency, and handling of the vessel. Some technical constraints were high rigidity with mostly single-skinned laminates, lightweight but also safe battery enclosure, and limited manufacturing capabilities and composite experience. So here I'm going to give you a comparison of the common structural approach and what we kind of decided through our investigation. So the common structural approach would be multi-part assemblies, heavy support substructures, exposed wires, external electronic enclosures, and separate functional compartments. But through our investigation, we decided that stiffness would be gathered through radii optimization, geometry surface continuity, and targeted carbon reinforcement. And now I'm going to hand off the mic to my colleague Rocco, who will tell you more about our design.
Okay, so a little bit about the design. So the definition of our design will be to integrate all the key components into one fully fixed cohesive assembly. So that means the cockpit, the battery systems, the steering system, electronics, and motor support structure would be, our goal was to put all that together in one monocoque assembly. The key requirements that we assessed that we focused on were the structural support for the driver, the battery and the motor, which we had to provide for them, and overall high stiffness and using less material as possible. We also wanted to achieve lightweight but rigid motor mount as well as a lightweight steering system. And our goal weight was below 25 kilograms, which we achieved. Our cockpit weighs exactly 25 kilograms without the batteries and without the motor. So our idea generated from the torpedo from torpedo, which originates from our hometown, but we also took a hard, long look from Formula cars and from aerospace industry. Basically, we focused on hydrodynamics and aerodynamics. We evaluated 3 different concepts: tubular frame, sandwich composite structures, and full carbon monocoque solutions, which we decided that this was the best one for our concept because of the maximum stiffness to weight ratio. So this is our design. As you can see, this is all one cockpit here, and it lays on two parallel tubes. All of the weight of the cockpit lays on 2 parallel tubes. We used carbon fiber composites and we placed a structural bulkhead behind the driver to ensure him some safety and for more rigidity. And we designed it with a lot of rounded geometries to provide even more rigidity to the design. As you can see here, this is our methods that we use, such as vacuum infusion, pre-preg manufacturing, and water jet cutting, etc. And as I already mentioned, we used carbon fiber, but for the bulkhead behind the driver, we used Kevlar materials because it's more fire resistant to give him some safety. We also designed our own Our own steering wheel, which we made for carbon fiber, and which has a quick release system. And we also designed our own motor mount, which is tested and it's good. After we had the final product, it was finally time for testing. By doing the simulation for all the races, we could work on our key results, meaning we could improve our trajectories and turning efficiency. We could refine our weight distribution by playing with the placement of the batteries, etc. And we could validate our cockpit rigidity and other stuff. For future improvements, we plan to work on optimizing our laminate layup for further reducing the weight, to simplify manufacturing and maintenance for access for the maintenance, because it's hard to navigate with only one opening here and the battery is right here. We also want to improve the airflow through the cockpit, also for the battery. And because the design is very simple and sleek, it's very easy to adapt for some other, for example, for some other races, some other categories of races. And our final product and finalization, the completed vessel successfully operates with 10 kilowatt hours battery system, 20 kilowatt electric propulsion. It has hydraulic steering, it has integrated electronic, and it's a very, very lightweight composite structure. And this is the evaluation. This is our team working on it. We also had our own homemade battery. This is our team leader and electrical engineer. We made it at home. And that's it. Thank you for your attention.
Thank you very much for your lovely presentation. I now open the floor to the jury for their questions, starting with Gilles.
Thank you very much. I have a question. Your philosophy behind your design was to have one single element making the stiffness. Is this working? Yeah.
Just my hearing.
Okay. So you wanted one single, let's say, hull making shape, making this stiff and lightweight, incorporating most of the components of the boat. Can you explain your choice of putting the engine support out of this main structure, which is making...
Engine support is actually part of the structure. I didn't present you well enough, but if you see here, these are two parallel beams which bend all together. They go all the way to here, and the engine support is fixed on it.
I understand, but the philosophy was that your skin was bringing the stiffness of your cockpit. So why didn't you extend the shape to
this?
Yes, because then it's two-part. Then you have the beams integrated into your skin. Others, you could have. Why did you choose to put those beams instead of using this?
Yes. You mean
the stiffness of the overall cockpit?
Because then.
What was your thinking behind it, and why did you make this choice instead of?
I understand. Then you mean if the part behind this bar would be empty, and when the wave hits at it,
then it's too short.
Yes.
I mean,
yes,
you designed it too short.
Yeah. No. It would be too empty, and we will have to put more layers of carbon or put some kind of structural element for it to hold it, and that would we would just gain weight with that.
Okay.
We will have to make it thicker, or we will have to
That was
place
the right
something.
compromise.
Yes.
For you.
And this is a good compromise. I mean, and with this design, it looks very sleek. It looks very minimalistic, which we aimed for, and I would like to say it's ready for mass production.
Thank you very much.
If I can pitch you an idea.
Okay, thank you for your presentation. Could you please elaborate more on the user experience, the user interface, about the ergonomics of the seating? I'm not sure if it was mentioned.
Yeah. That part, the seat and everything was made everything was basically made for our driver, for our pilot. Our pilot is 62 kilos and he's this tall. So our seat and everything is made basically just to fit only him. And he can move freely in it. He can reach all the way in the back if he wants. He can climb on it. He's free to do anything inside of the cockpit, if that's what you meant.
And also for the interface, what does the driver see? Is he provided with any information or any data?
He can see everything. He can see the nodes. He can see the power output. He can see the temperature of the cells of each and every cell. And we also developed a little app for seeing the trim here. And yes, that's pretty much it.
I think we have time for one last question.
Good afternoon. One more question. Out of curiosity, could you give us a breakdown of the number of hours you spent between styling, engineering, production?
Because we are a really small team, we don't have, you are doing engineering, you are doing structural, you are doing CFD, everybody is doing a little bit. And everything we are doing it on the go. And everything is trial and error, everything. But some things cannot be done on trial and error, like batteries, like structural things, some things. But basically, the technological stuff in the workshop have been done in like the vacuum infusion and stuff. It were also trial and error, but possibly like maybe 2 to 3 months. Then after that, it comes polishing and everything. Before that, the engineering and the design of the cockpit took probably, 5 months. I don't know how long it took for the conceptual part, because I wasn't there. And with this I wasn't also part of that, so I don't know. And the electrical stuff, the battery, it took 3 months. That I know. The battery took 3 months because our electrical engineer can answer you right there if you want to know about the battery. He can come on the stage if he wants.
Thank you. The whole design and production took us around, I would say, 8 months, but the motor mount was made the next year. So this was an addition to the already made design. So let's say, 8 months for the whole thing to work completely. Sorry? Okay, if we added that, it would be better. Yeah, I understand. I don't know if we have it right now, because as my colleague said, we are a small team, so we just do what we have to do to get there. We don't have much time to actually write each and every step down, take measure of the time and everything we can approximate. So we started this, I would say 2 months after the previous year. We had another boat in the energy class, and then after we finished, like 2 months after that, after everything settled down, we started making Wilson, and then it was finished like 2 months before the next competition. Thank you.
Thank you very much for your presentation. I would now like to welcome to the stage Swiss Solar Boat with their Eco-Conception Prize.
Hello everyone, I'm Archibald from Swiss Solar Boat and I will be presenting the Eco-Conception Prize today. First of all, let me talk about the first prototype we have, which is called the DAU. It was a prototype using PV panels, 6 meters squared, 1 person on board, 13 knot cruise speed and 7 kilometer autonomy. This was our old prototype, and actually we came to Monaco in 2021 and 2022. And we won in 2021 the Eco-Conception Prize with this prototype. Why? Because we worked on the mold we were using, only a quarter of mold thanks to the symmetry, triple symmetry of our hull, and we could reduce our emission thanks to that. At the end of the lifetime of this prototype, we could perform an overall LCA, and what we discovered is that once again the carbon fibers and the carbon fiber mold remain the highest impact factor. That being said, in parallel, we were developing the next prototype, the Lobster, whom we were participating this year in the Sea Lab class. As you can see, the specification, we have 1 pilot, 2 passenger, 160 kilometers autonomy, and 25 knots cruising speed. So it's a huge step up. Because of this, we need to find a trade-off between the emission that we want to keep low, as always, and also the mass of the boat that we want to keep fairly reasonable. Because if it's too high, we won't be able to reach those improvements that we are seeking with this new prototype. How we managed to do that? Well, mainly thanks to the scaffold production method that we have been developing, that I will be presenting to you right now. So instead of using a carbon mold, as you do in the traditional method, we decided to do a bit differently. We started with a regular wood scaffold, as you can see here. And then on this scaffold, we decided to stamp plywood, okume plywood, which is the one we're using for our boat. So our boat is made of carbon, wood carbon, composite sandwich. And then on this okume that has been stamped, we do the regular infusion. What is really important to understand is that this okume is then really becoming the hull of the boat. As you can see, regular infusion, then we're going to glue the 2 sides on the keel line, turn the boat upside down, do the infusions on the other side, and you get the beautiful hull that you have on the bottom right corner. What you need to take home about this production method is that at the end, we were left only with the scaffold that you can see here, and we could just throw it away in the recycling bin, thus avoiding the emission due to a carbon mold. Now, let's see the figure. On the left, you can see dark blue what would be the global warming impact, in light blue what is the weight, and we're comparing a traditional method, the method we use, and a boat made of full plywood. As you can see, in full carbon, of course, the emission is very high and the weight of the boat is low. And if you use full plywood hull, you have less emission, nearly 0, but you have boat that is a bit with a high weight. We are in the middle with a 85% reduction on the CO2 impact, but plus 15% on the hull weight. That's the trade-off. And this plus 15% on the hull weight, it translates in plus 3% in the total weight of the boat. Maybe some of you are asking the question, okay, you're using wood, but where does the wood come from? We have asked ourselves this question because of deforestation issues, transportation, etc. And we decided to work with a French manufacturer called Joubert. They use Okoume plywood from and they have PSC and FEPC, which are in simple words, Sustainable Management Forest Criteria Assessment Certification for wood production. Now, what about feasibility and scalability on this method? You can see on the right the overall impact, not only on the hull, but on the production of the boat entirely. We have minus 10% on our emission using this method. What about the workload? We assessed that we had a 28% workload more than if we had to use the traditional production method. Regarding the best market fit, well, it's great for racing prototype, custom research boats, maybe for small series, but for mass production, for now, it's not the more convenient because of this workload. To be honest, on that point, it was the first time we were doing this method. We developed it, so of course, we lost a couple of hours trying to figure it out. Maybe that in the future, if we work more on this production method, we could find a way to reduce this workload actually. Let's have a look at the overall LCA now. Let's try to break down this figure. So we can see the end of life and the use phase. The use phase is actually only the Monaco Energy Boat Challenge in the LCA. The production, still 95% of the overall LCA with the structure. Despite our efforts, still nearly 50% of the emissions. Regarding the hydrodynamics part and the fuel cell, here, because of the use phase being only the Monaco Energy Boat Challenge, they cannot really benefit from the fact that you have a reduced consumption when you sail with those. Maybe to mention the PV panels, 1.6% for a single component, that's a lot, but actually we're aiming at using them to produce electricity and then do what we call vehicle to grid or vehicle to load, which means selling the electricity to the grid or producing directly hydrogen with it. Well, the big question, did we have an improvement between our last prototype, the Daewoo, and the new one? We decided not to compare in absolute value the CO2 emissions, but to have a more fair comparison. We divided by the kilometer of autonomy, 7 for the Daewoo, if you remember, times the person on board, 1 for the Daewoo, and kilometer of autonomy times person on board for the lobster, which means 160. Times the 3 person on board. As we can see, we have a 5-fold reduction, so that's very important for us. It's easy with buzzwords such as hydrogen, foils, or PV panels to think that you are sustainable, but it's always more complex, and we're very happy that we could assess with a scientific procedure that we indeed made improvements between the two prototypes. I will now conclude on what is just said. The environmental advantages, we have almost minus 11% of the emission on production of the overall boat. If we compare of boat using the traditional methods of production, we have a 5-fold reduction compared to our old boat, our previous prototype. And what are the trade-off? Well, plus 15% of weight on the mass of the hull, but that's only plus 3% on the total mass of the boat. So that's a fair trade-off in our opinion. And plus 28% labor augmentation, for labor production, which could be reduced in the future if we had to further develop this method. That was Swiss Boat. Thanks for your attention.
Thank you very much for your interesting presentation, and I will now open the floor again to the jury.
Thank you, first of all, for a really clear, concise sort of explanation of some of the insights that you found. I guess my question, I'm assuming, I think I know the answer to this, but when it comes to the production of this mold. You've mentioned that there's a reduce in impact. You've also mentioned that there's an increase in workload. But financially, what was the savings when you are, or not savings, increasing it compared to like a carbon hull mold?
Yes, so as you're not producing a carbon fiber mold, you're just saving all the carbon fiber that you're supposed to use to make the mold, so you make enormous saves on this side also. So it's clearly cheaper to do this with our method than the traditional one, because you skip this part, which is expensive, because usually, to be more technical, when you do molds, you want to put more carbon fiber to make it really stiff to resist the process. So it's usually expensive, the carbon fiber molds.
If I might complete, I think that it's less expensive regarding the material you have to use, but because of the workload augmentation based on the salaries in Switzerland, we conclude that it was not less expensive, it was cheaper actually, and that's why the further development on reducing the workload could be interesting on that aspect.
Yeah, super interesting. I don't know if anybody else has a question.
Congratulations for the job done. Could you please go back on the previous slide, because that's a key number I want everyone to have a look. It's
sorry,
I think that's the other way.
Okay.
Yes, when you say the amount of CO2 per kilometers per people.
This one?
Yes, this is a key number that we have all to figure in this whole industry, because if we want to design boats all together, we have to have a clear target, and I guess the amount of CO2 per kilometer per people, this is exactly the number we have all together to think about and have an highlight. So my question is, are you able, to compare this number compared to other vessels that exist? For example, you are coming from Switzerland. Could you compare it with the boat that's crossing the lake in Switzerland? And you can give us some example of benchmark from your boat compared to other boats that are transporting people.
Yes, that's too bad, because on the other presentation I have the figure for that. But compared to the Navi Express, so they're using, as of right now, diesel hybrid battery boats, and with that we're performing better. But we calculated what would happen if they integrate a fuel cell, and that would do a major reduction on the impacts. But for the benchmarking, like if you point out any boat, I'm not sure I can answer that. Sorry.
Also, very impressive presentation. And
Thanks.
I'm curious on the wood, if you know the traceability, the origin of the plywood you used, from which country it's coming from, and if it's included in the LTA.
Yes, so we know that. I'm just having a black hole right now in my head. It's the Congo. It's from Congo, sorry. And I did not mention, but also the supply chain traceability from the French manufacturer. It's very detailed. That's one of the reasons we chose it.
Thank
you. You've also obviously used a lot of plywood in the production of your mold.
Yes.
But I guess my question for that is that I'm assuming at the moment a lot of that's going to be waste at the end. Is there a consideration for how that can be built modularly so that you could develop or adapt it for changes in your production cycle?
Yes, to be honest, we didn't want to show them because they're a bit ugly, but we recycled them by making some IKEA cupboard, no, not a cupboard, shelves, sorry, for our warehouse. And so we used a lot of the remaining wood to make shelves, to be honest, so where we can stock the resin, the carbon fiber rolls, scotch, electrical cables, everything. We did not use all the wood, of course, because it's a lot of wood, but we used quite a lot for this.
Thank you. Thank you very much for your presentation. Thank you. Thank you. I would now like to welcome to the stage our next design prize with Team Cshaki.
Thank you. 26 states, countless languages, and a very rich cultural heritage. And we are the only country in the world to have an ocean named after us. Greetings, everybody. This is Vishruti Praveen Kumar, and this is Reshma Sharif from Team Cshaki representing India. The legacy of Kumaraguru institutions has 40 plus years of academic excellence in agriculture, technology, management, and liberal arts and science. And we are one of the top 5 universities, institutions in the nation known for our research. So when we were looking to give a face to our boat, we did not just want to select something very random or something that will only look good in the photos or to the naked eye. We wanted to take inspiration from something which is going to get highlighted in our performance as well. And this year we have not one, but 2 inspirations. One is from a fauna and another one is from an engineering aircraft. So the first one is Megalodon. It is one of the largest fish sharks to have ever existed. And there are 3 main points why we took this as our inspiration. It's because of its hydrodynamic efficiency, streamlined form, and how commandingly powerful it is when it is in water. And the second one is from an aircraft, and this was majorly taken as an inspiration for the air ducts. And we've used only 10% of this inspiration in our boat, while the rest 90% is from the Megalodon. So after 1,000 sketches, 1 million reiterations, and again, a lot of changes, we have derived our sketches. These are our sketches. And as I mentioned previously, 90% of the body of the boat is taken from the inspiration of Megalodon, and the air duct's inspiration is from the aircraft. And this is the form of our final cockpit. So in order to build the final cockpit, we have taken only a few lines from the sketches that we've derived, and these are as follows. So presenting to you Yali 5.0, one of the most faster, sleeker, and smarter boat of Yali. So one of the main things we kept in mind while building our boat this year was that we wanted to reduce the drag, because that was one of the problems we faced last year. And I can say that we've made a commendable change by reducing almost 10 newtons, and our value right now is 8.5. And the coefficient of drag also we've reduced very, very well, and it is only 0.02. So to validate, of course, our work, we have taken a lot of these CFDs that you can see. So the first one is we wanted to know how well the air is against the surface when it's on water of our cockpit. So the first one is of the cockpit alone without the pilot. Then when we did the CFD, after doing the analysis, what we understood was that in the top middle section, there was a lot of air that was passing through. So we wanted to tackle that as well. For that, what we've done is we've introduced air ducts to it, and that problem has been solved now. And finally, as a result, we have reduced drag efficiently, and also there's a stable airflow circulation. So whatever we are building now, whatever we are doing, it's all for the purpose of human beings. And we wanted to keep that as one of the major focuses, that our pilot should be able to comfortably access everything in the cockpit, and he should be able to have a very good control for, obviously, the better performance. So keeping that in mind, with an 170 centimeter pilot, we have the seat back angle is 10 degrees inclined to the forward, and the seat pan angle is 15 degrees upwards. Again, to validate this, we went through the ruler assessment, and we got a score of 2, which again proves that we have validated it very comfortably, and the controls are precise. And now talking about the material composite, again, we kept another thing in mind over here, that we do not just want to select a random material composite. We wanted it to be sustainable. We want it to create an impact in the future. That's why we targeted the natural fibers. And for this year, we've used a combination of the hemp fiber along with along with the nanocellulose. So the nanocellulose is infused with the hemp fiber. Why nanocellulose? A lot of you might ask. When we look at cellulose at a nanoscale, it is we can easily get all the breaks covered, and it makes the material even more stronger. So this stronger version helps us withstand the thing that comes against us in the waters. And we've also used a layer of carbon fiber because this hemp fiber and nanocellulose is an R&D of ours. So to withstand the dynamic races, we wanted one layer of carbon fiber as well. And again, to validate that, we have undergone 3 tests, and these are the results for that.
I believe design is not only about cockpit, but it is also about the system entirely. And that is why I'm here to talk about the system as a whole. The propulsion system, the system which makes the boat move forward in the first place. We had designed a counter-rotating propulsion system with speed propellers, which is of 15 inches, and efficiency propeller, which is of 12 inches. With an overall, it decreases the slip by increasing the efficiency and the overall performance of the boat. To talk about an overall with the propulsion system, it is made up of a spiral bevel gear while having again a counter-rotating propulsion system with custom-made propellers and also hydrodynamically integrated. And to specifically mention, this makes with the pilot's easy handling with the steering system, which becomes much more safer and comfortable for the pilot. To talk about our energy system, the battery that is shown here is what we do our testings with, and we have made a 3-pack module battery pack with integrated cooling system, and we've also designed a custom cell stack holder which holds the cells in place, and we have made a PCM material which is of paraffin and expanded graphite, which will have an perfect thermal conductivity in the battery system, and it is under R&D, and we hope to bring in a boat next year. Showing the thermal images of a battery while we were testing it, and these prove that with PCM, the battery performs much better, and the heat conductivity and the thermal management is much more efficient and effective in it. We're coming from India, very far away to compete here, and which is a huge thing, and we're very proud to be here as well, and showing that the cost is much more while we participate over here. And this is a projection of how much it costed. And thank you so much for your attention. We have given a QR code. Please scan it to know more about our iterations that is taken for each of our design. And lastly, thank you MEBC and Yacht Club, the Monaco, for giving us this opportunity to present here.
Thank you very much for your presentation. I'll now hand over to Gilles.
Thank you very much for your presentation. Your design has been it's really linked to the nature. You mentioned the megalodon being your main inspiration. How these sketches and the final design of your cockpit has been influenced by the engineering, so making the link with, it was really like making it looked in your presentation that you've designed first and take a lot from this inspiration and a lot less than what are the parts in your boat, and how you connect the styling or the shape of your cockpit towards the integration of the components.
So, sir, I believe your question is that the cockpit, the inspiration is not understood properly. Am I right?
No, my question is, how do you relate the different step of evolution of your design towards, you've probably mentioned the aerodynamics being an influence in your final shape of the design, how all the other parts are participating to the final design of your cockpit?
Okay, so Last time we were using our split up cockpit actually. So comparing to last year's cockpit, we wanted to push it into a monocoque cockpit. So after many analysis and many steps, we were noticing that the CD value and drag value is getting reduced in the monocoque cockpit. So we have designed in such a way that in each and every iteration, we noticed wherever the drag is there, we have changed the design according to it. So finally, from the inspiration of Megalodon and from the fighter jet, we have taken the design inspiration and we have implemented according to the aerodynamic, and we have implemented in our cockpit.
Apologies, thank you. And the next question?
Okay, thank you. I really appreciate the sketches, the mood boards, how the project started. That's usually how the design process works. The next step is usually the prototyping or the mock-up stage. So I'm curious, what type of tests did you do? How did you validate your simulations into reality to then make your final?
Okay, so we have actually tested the materials. So like for example, we have tested the flexural test, tensile test, and the displacement test for the cockpit. And also after the values which we have attained, according to it, we have actually implemented the materials in our cockpit. So this time we have used the hemp fiber and nanocellulose. Comparing to the other fibers, we got to know that these fibers will be much more better for our requirement. It's not like over-engineered or not least one also. So we have actually got the values after testing, and also we have applied it in the analysis, and we have got the result in the end.
And for the seating ergonomics, so you have done the calculations. How did you further validate that when you physically made a prototype?
Okay, so our pilot is actually around 170 centimeter. So we have actually done it in the Rola assessment. Like we have assessed his we have actually sketched his body in a design way, and we have done a CAD model, and we have inclined the seat angle to 10 degrees and also the upper thigh angle to 15 degrees, which makes him more comfortable in our boat.
Thank you very much.
Thank you.
Thank you. Would there be one quick last question? No? Thank you very much to the jury, and thank you to the team.
Thank you.
I am now happy to announce Hainan University with their Eco-Conception Prize.
Madame and Monsieur, bonjour. Hello everyone, we are from Hainan University, and I am be honored to report our about life cycle assessment journey. First, I will introduce our project. Our fuel frame was built by a carbon fiber tube, and we hand-lined and hand-dried with not glue. So we can also disassemble it after race. We can disassemble them and to the shelves or desk. It's not only recycling, but also upcycling. The next one is what is a life cycle assessment. It can openly communicate our project's environment footprint and identifies the hotspots for future optimization. And next one, in our project, our system boundary about 6 parts. host structure, propulsion system, electrical system, control system, and hardware system and excitation. In our structural carbon fiber deck and the electrical system, we use solar panels and battery. About the propulsion system, we use e-propulsion motor battery. The next part is about what is included. The most included is our transport distance. So about transport details, from Haikou in China to Monaco, distance about 9.5 thousand kilometers, and about the return journey about 18,000 kilometers by sea flight. So it takes about 12 hours from China to here and 6 hours difference. So it's not very easy for us last weekend to come here. And this is our date street. First, primary date street about sponsor specifications and direct measurements. The secondary dictionary about mirror shift and peer revision literature. So our main data quality assessment about 3 parts. First, about sponsor compounds and customer built compounds and purchase standard parts. Here our assumption about first transport distance and material-wise, use phase in energy and end of our life. So we have 3 decisions. First decision is battery chemistries, LFP vs NMC. So we assume that the e-propulsion E113 LFP battery has a lower cradle to get the environmental impact than a conventional NMC battery. And the results we can also show. Our LFP battery has about 35% lower production emissions compared to CO2 eco for standard NMC battery. And finally, we decided to choose LFP battery so that the emissions reduction. The second decision too is about structural material. We choose the carbon fiber and VS aluminum. We choose to use carbon fiber to build our boat frame. We use tube. The wide saving of carbon fiber refers to we offset its higher manufacturing emissions, leading to a low overall life cycle impact. Like showing the picture, the results also show that CFRP frame has about 26% lower total emissions, 99.9 kg CO2 equal with 135 kg CO2 equal for aluminum. So final decision, we chose carbon fiber tube frame. This highlights the importance of our circle series. And the decision 3 is about the transport mode. Yes, it's the sea flight about 4 to 5 weeks from China to here, but we needed to meet the 2026 competition requirements, so we chose the air freight outbound from China to Monaco. We acknowledge the environmental potential and committed to design fuel sea freight into future project timelines. So that's about our heart of our vessel propulsion system. We chose e-propulsion battery and e-propulsion motor. As the recycled content of this specific compost is not publicly disclosed by the manufacturer, so we assume zero recycled materials in our analysis to maintain transparency and avoid overstating statistical benefits. And that's about our solar panels. We also modern process enable recovery of up to 19 to 95% of glass and metals. About the sustainable future beyond the race, we focus on the end of life. We can state the exhibition displayed at our university, public events to inspire the future energies, and foster interest in the marine technologies, and then we can keep the vessel in a controlled environmental for potential reuse in the future. The next part about our safety disassemble our boats, because our boat is assembled by the carbon fiber tube, so it's very safety to disassemble it to the and we can reassemble to desk or shelves, so we can recycle it. And the last panel is about end of life. It's a circular economic approach. So about carbon fiber, we can, yes, let I say, we can use it to to reassemble it to shelves or desks that will environmental friendly. This is our overall LCA results. Total cradle to grave global warming potential, we cost about 1.29 ton CO2 eco. And the next environmental impact is 3.04 ton CO2 eco, excluding the mandated outboard air freight for official competition ranking. So in the future outlook, we should update the logistic plan for fuel sea freight in future competitions, and the circular materials emergence recycled carbon fiber alternatives, and share knowledge inspire the wide engineering community. So we have built a fast boat, but more importantly, we have built a responsible one. Thank you for your attention. Thank you.
Thank you for your presentation. I will give the microphone to Lizzie, who will have a few questions.
Firstly, thank you so much for your presentation. One of the questions I want to see, you mentioned the different battery chemistries that you looked at. You've mentioned what the sustainability difference was between them, but what were the trade-offs? So was it more challenging to work with? Was it a different energy density? What were the trade-offs between the decision that you made?
Okay, I think I give some background information. Actually, he is my student. So just less than 2 months, we decided to join these challenges. Actually, even before, I haven't done such a design. Not to mention the student, all of them know any idea about that. Then we'll see if you are interested in challenge. If you do, then maybe around 40 days, we have to do something to join this challenge. So then, what to do? I just enjoyed the first meeting, discuss with you. Then you do that, I pay that. Then working are yours. So then think about how to quickly to do that. So traditional design model, we don't have financial cost for that. Also, no enough time. So then finally they think about just use truss structure. Or trust. If you look at this, because this is the earlier first PPT. If you can see, all of them just a tube type carbon fiber truss structures. So very light, but light is not advantage. Maybe you have to think of the balance, the force, and other dynamic characters. So they do all things from design. Also think about the battery, how to compare the different batteries. So if we even think about the hydrogen ecology, hydrogen energy, and also solar energy, but actually for such a challenge, they are all the only batteries is not enough. So we have to think about still use the Li batteries, then combine with the new energies. So I just give such a background. Thank you.
Thank you. So yeah, I guess the thing I want to understand is that with you've mentioned sort of the carbon fiber hull, and you've mentioned the batteries.
Yeah.
There's obviously going to be challenges in making those decisions, but I want to understand a bit better what the challenges were that you came across when you came to that final decision. So was there a weight, for example, weight difference or a energy density difference? But to choose, what was the path that you took to make that final decision?
I think the first issue is actually financial cost, because the student asked me, then I say I only have roughly 30,000 euros. You have to do all things, including your travel, all together. Just such a money give them to do such things. So they have to use cheapest way to think about it. So only the except the bottom sides is the club provided. Then all other things think about just truss structure, carbon fiber. Then some just formal. Then do all things together. So even an engine, we get just get an older engine from the other boats used for this one. The challenging thing is the energy, so the power battery. Also, we don't have time and also have financial support. We haven't asked the company to support that. So I think about how to better use the current the battery technology, incorporate the new energy. So new energy just a sustainable way. But we more think about how to environment friendly, sustainable development. So after this challenge, we take apart all things, just a small tube. Then they can use another boat or use different fields. So you don't no any waste. Thank you.
Perfect, thank you.
Unfortunately, we've reached towards the end of the Q&A time, so I will thank you for your presentation and your answers to the jury's questions. Thank you. Thank you very much. Congratulations for your presentation. I would now like to welcome to the stage with the Design Prize 1C Energy team.
Hello everyone, I'm Theo and this is Johannes, and we're here to present the vision of 1C and of the Technical University of Berlin. So first of all, we wanted to talk about our core challenges that we faced during the design process, and we divided this into 4 main parts. First of all, we wanted to reduce waste, because this is of course an important factor in terms of the design that we want to integrate into our boat and into the races. At the same time, we wanted to optimize the weight, and doing that through structural components and through optimization all along the design process that we had to go through. The third core challenge that we had was, of course, a cost reduction, because a design without a successful cost reduction isn't a sustainable and futuristic design that we can implement on the bigger stage. And finally, it is really important to have an innovative and sustainable design to be able to compete in the future, and also to develop new concepts, to have the implementation of materials, and to test it on a bigger stage.
So the material choice is very important because it is the core of all of the designs, and it's not only important to have materials that have a certain strength, or but it's also very important to think about the sustainability aspect of it. So naturally we implemented some wood. We implemented some aluminium because it's very cost effective, reliable, easy to shape, and corrosion resistant. Also some flex fiber. Some other teams also mentioned that they use that for the hulls. That's also a very good material. Some PTG filament, and this is something that we want to implement next year, is mycelium, a biodegradable and lightweight material that we can organically grow inside of the cockpit. This will be mentioned later. It is a project for the future. So let's start with the energy sources that we have. So we have the stacked batteries. Oh, okay, the laser pointer is not working. So we have there the battery packs. These are modular removable battery packs that we can use, put in and out. We have that. We got them from our sponsor and are working with them. They're really convenient for modular and flexible designs. We implemented here into the energy box. Yeah, so here we have the second source is the solar system. We have eight units that deliver 800 watts, and with that, this is optimized for the endurance race. So we can be where we have as an extender of the range. So on the motor design, we also used custom dual prop to have a smaller gondola. So the component down here. With this, we are able to have less drag in the water, so this improves it. We also used 3D printed structure here to improve for the drag as well. We manufactured the motor ourselves. We needed to implement around 100 parts. Some were bought, some were professionally made or custom made for us, and some were self-machined. For example, we used welding. We welded aluminium gondola in order to not have to carve everything out with the CNC machine. And we also used a special stainless shaft in order to be corrosion resistant. This is also a key component of our design. So we designed our ship to be, of our boat to be modular and adjustable. So we have the aluminium frames that are cut out for the weight reduction, but we made a lot of holes to be able to switch around and move the components depending on our needs or on the different seasons, so we can then recycle it. We, for example, used to have a foiling system that we could add. Now we don't use it anymore because the rule changed, so we can kind of switch and add and reuse it. I'm passing to Theo and I'm passing you some material to have in hand.
Okay, so for this year's cockpit, we tried to go for a different sort of approach because we wanted to have something new. Something new means that, for instance, if you look back to last year, we wanted to have some changes, but not only changes in terms of length or in terms of structure, but also in terms of materials. And that's where our new design is coming from, because in collaboration with our sponsor, we started to imagine a new way of shaping the cockpit by implementing a new material. This year we 3D printed all of it with our filament, and if you can see here, we have different parts, and all of them were 3D printed, all to prepare for a second phase that we want to implement next year, which will be the implementation of mycelium, which will then replace the 3D side of our cockpit. So, talking now about the human interface and the ergonomics. Of course, this is a really important step or really important approach in terms of design, because of course a pilot needs to have a proper cockpit in which it's really easy to, for example, navigate on the sea. That's why we have a custom throttle level on this side. At the same time, we have an IT box with a large touch screen that can easily be used to observe sensors and to have all sorts of parameters on it. And last but not least, we have a customized, adjustable, comfortable old wooden seat that got implemented to this year's design, just to make the most out of the cockpit for the driver. So, talking about the 3D. You can see here that we have divided the whole cockpit into different parts that we then just stick together to make one cockpit. And if we can look at the 3D printing process, you can see that we started with on scratch with some 3D cockpit design overviews. Then, when we were satisfied with the parts, slicing them into slicing the model apart. Then going towards the printing process, which had an average of 8 hours per single element. Going further then to the whole process in which we had to gather, sort the raw elements, design by screwing the parts together, assemble them with the wooden structure inside to make it stable too, and then at the end of all the processes that we had, we could have done a final assembly of the cockpit, and therefore do quality checks, signing it off, and we are doing this cockpit to implement the whole mycelium into the whole cockpit next year. And if we put all of this together, all that we have said, this is our rendering for this year. You can see it on the paddocks on the first stage, and yes, this is our design, and thank you for your attention.
Thank you very much for your presentation. I will now pass over to the jury for their questions.
Thank you very much. Thank you for your presentation and thinking ahead of the future. So you mentioned the ergonomics of the pilot. Just jumping on a detail, you mentioned the custom throttle. How the ergonomic intervened into this custom design of the throttle? What has been your connection to the pilot to optimize the throttle to make it custom to him?
Oh. So we didn't design the throttle for the cockpit, especially for the pilot, especially. We just like custom made it on our own. We adjusted the position so that it's more convenient for the pilot to rest the arm and have the control. For example, for the endurance race to be more ergonomic, but we did not adjust it to our pilot specifically. This was the question, right? Oh.
No, I was not talking about the individual, but the pilot.
Okay.
A pilot.
And also at the same time, it's 3D printed also.
Yeah, I understood. It was 3D printed, but there is nothing which is fully related to the way that the trimming of the throttle is not, in a way, way special than regular throttle. It's just the positioning and the sizing, dimensioning of it, which has been slightly improved, right?
Yeah.
Yes.
Exactly.
And yeah, just another question from the aesthetical point of view. The global design approach is very well. The fact that your concept is very modular and adjustable to any of the future development is really good. The cockpit itself is really a small part of your entire project. So let's say, what is the inspiration then on the cockpit shape, or is the shape being driven by or limited by your manufacturing process or not? The way the assembly that you've made is, but it's bolted. I see some holes, so expecting some bolts.
The thing is, for the cockpit design, why we first started with the cockpit, because we thought that it is the easiest approach towards the whole frame that we have to implement a new material, and in this case it will be the mycelium. And in this case we wanted to first start with the front part and then move on, and maybe later on maybe build also the frame or other parts or components that are in the whole frame out of the material. But we need to find a starting point, and this point is, we believe, the easiest for it.
But is the mycelium as influenced the design itself of the cockpit? Because this is where the starting point of the use of mycelium in your project, and is this material has an impact on the way the cockpit is designed?
Yes.
Yes, because of the modularization. Our plan is for the next year that we build the whole cockpit aus mycelium itself. But the production line is really takes a lot of time. Like, it takes 3 months to grow the mycelium, and this was not we wasn't able to do this. So our idea was to adjust this idea and build the modular parts, and then we found out it works, but now we have to adjust to the mycelium, so build up the frame and combine this together.
Okay, thank you very much.
One last quick question from the jury.
I actually just wanted to ask about how you're going to be implementing the mycelium into this. Are you going to grow it directly into your 3D printed structure, or are you going to use a mold? How are you building that in?
Well, we're going to use a mold, which can be 3D printed. Right now, it's a mixture of wood and 3D printed parts, which are modular together. We build the negative form, then you can grow up entirely, then you can heat it up and do the detailing, so the color, and print it itself.
And will you laminate it, or is it going to be?
No, it's going to be waxed, because we wanted to imply less waste. So we want to do this biologically and using beeswax, so the mycelium can still shine and the design can be still seen through the whole cockpit. It looks similar to wood because the structure itself, usually it's made with sea dust, or you can do this also with coffee. Yeah.
Cool. Looking forward to seeing it next year.
Thank you very much, and thank you for your presentation. I now look forward to welcoming to the stage Uniboat with their Eco-Conception Prize. Thank you.
Good afternoon, everyone. We are the Uniboat team, and we are going to present our eco-conception for this season. So, as you all know, nowadays the focus is on developing more efficient and lighter vessels. But as the world aims to get greener and greener, it's very important to give the right value to the materials choices. That's why this year we've worked as a team to implement on our boat recycled carbon fiber, hemp and recycled glass fiber, flax fiber, and sodium-ion batteries. So starting from the new cockpit floor, this year the cockpit floor is made of recycled carbon fiber instead of the expired virgin carbon fiber of last year. This caused a slight increase in the weight of the cockpit floor, because we had to increase, to add a little bit of material in order to maintain the same mechanical properties of last year. At the same time, this allowed us to reduce the energy consumption and the environmental impact. In this slide, we can take a look at the mechanical properties of recycled carbon fiber. So in the graph, we can see the greenhouse gases emissions, the comparison between virgin and recycled carbon fiber regarding the thermal recycling process. So for each ton of fiber, the virgin carbon fiber emits 29.45 tons of CO2, while the recycled one emits just 4 tons of CO2. So this corresponds to a decrease of almost 85% of greenhouse gases emissions. Moreover, up to 70 to 90% of the original mechanical properties are retained, and the slight decrease in the mechanical properties is due to both the thermal recycling process itself and the fact that the fibers become shorter and non-continuous. Although there's a small decrease in the mechanical properties, the recycled carbon fiber still provides sufficient performance to meet our structural requirements. Moreover, we also have about a 40% reduction in the cost. In these graphs, which are that we made through Marine Shift, we can analyze the comparison of the life cycle assessment of the cockpit floor in 2025 and 2026. So from the first graph, we can see that the impact of global warming fossil was reduced to almost 1/4 compared to the last year's value. And in the second graph, we can see the contribution to global warming non-fossil, which was reduced to almost 1/3 of the previous value.
Then we worked on the battery box supports that was previously made in carbon fiber. But this year we decided to do a bio-based composite made of recycled glass fibers obtained by dismantled vessels, hemp fiber and red algae, And the core is not foam, but it is a recomplex, which is a recycled thermoplastic polymer. As you can imagine, the natural fibers has very much lower performance and mechanical properties. And that's why we decided to use a composite, using at the same time glass fiber and flex hemp fiber, to reach a compromise in which we were minimizing the decrease of performances while still having a lower impact on the environment. And as we can see from these graphics, we have actually a negative CO2 emissions due to the fact that hemp actually absorbs CO2 from atmosphere, and that's why it is negative in relation to the battery box supports in carbon. While for the energy consumption, it actually was decreased by 84% from last year. And then we had another modification that was in the engine strut. With the help of the designing of computer, with the engine strut, it was changed from carbon fiber to flex fiber, and then helped us reducing, saving the non-renewable energy up to 90%, while actually reducing the global warming fossil impact to 90.5%. And we can see how much the energy consumption was decreased, decreased, and the global warming fossil was also decreased. Right now we're trying to search and developing the sodium-ion batteries as an alternative to lithium-ion ones. And this is a much greener choice because the sodium is much more abundant than lithium, up to 1,000 times. And it doesn't require the use of nickel and cobalt. And also another important matter is the fact that to extract sodium, it actually needs up to 78 times less water than the lithium extraction requires. But of course, there are some drawbacks, otherwise we would just use the sodium-ion batteries. And the bigger problems is the fact that lithium has a much higher energetic density than sodium. And that's the problem that we're trying to solve, and we're hopeful to solve this problem and trying to implement sodium-ion batteries for next year in our boat. Thanks for your attention.
Thank you for your presentation. I'll now hand the mic to Lizzie.
Thank you for a really great presentation. It's super clear. It's good to hear some of the different materials that you guys are utilising. I was wondering if during your production processes, if there's anything that you were doing to reduce impact in your production methods as well as in your materials that you're choosing.
We tried actually to have like the mass of all like the materials reduced as much as possible, and for the matter of the even engine strut, we also tried to use like 100% of flex fiber, but it was not possible for complication in the lamination process. So we had to like use a hybrid component with flex and a little bit of carbon fiber. And so it was all about compromises and tries to work in the best of the performance while still try to have the greener solution as possible. But of course, the performance was always like a little bit lowered, so we tried to save that as much as possible.
I have one other question as well. With your recycled carbon fiber, do you get it from a sort of specific supplier, or are you recycling it from your own projects? Where are you getting this recycled carbon fiber from?
Well, about our recycled carbon fiber cockpit floor, it was manufactured by a partner company, and it was made in Italy. It was produced in Italy from a very new recycling company, a recycling carbon fiber company, and that's it.
Thank you.
Yes, that's wonderful to see that having the Marine Shift 360 in the past year and this year, you can compare the evolution, what you have done. Could you please share the idea about optimization for the coming years you have in hand now? After having working on the boat this year, what are the new evolution you are considering in order to have a better impact for the next year?
Well, about possible future implementations, we are considering to redesign some of our components using, again, recycled carbon fiber, since we noticed that despite a little weight increase, which is not a very important weight increase at all, it is possible to have a great reduction in the carbon emissions. And maybe we would like to work on the use of more natural fibers. As you know, we already have our cockpit made of flex fiber, and the supports are now made in hybrid recycled glass fiber and hemp fiber, but maybe we may work on producing, for example, our cockpit attachments with some natural fibers, or maybe a recycled carbon fiber.
If I understand correctly, this year you are having a sodium battery in your service battery. But next year you are really planning to get really the main source from sodium battery. What probability do you think you will come next year with full sodium?
Okay, we don't have it on board right now. We worked on it for the whole year, but unfortunately we were not ready and we were not on time for the race to put it on board. And so there's a high chance to have sodium-ion batteries on board next year, but not for our full powertrain.
Thank you. Would there be one last quick question? Thank you for your presentation. I am happy to confirm that there's going to be a short 5-minute interval break for the jury. Thank you. We will start the session again at 5:35. Thank you.
Just a dream, but it lingers, it lingers. Ourselves in a moment when I'm old. I'll think about the time when we were all in, staying up all through the night until the morning. How it made us feel alive, where did the time go? Guess I watched it slip away, the lights go out. Say goodbye, my love, and just let me go. Oh, your heart is all that I've ever known. I'm still holding out for a miracle. I'm caught in the crossfire, in the crossfire.
Quel est le sens de notre démarche collective? Monaco, capital of advanced yachting. La performance sportive se cultive dès le plus jeune âge et je suis convaincu que le sport est l'un des piliers de notre société. Lancement de la belle classe de son centre de formation. Je souhaite que nous maintenions le cap avec enthousiasme, passion et détermination. Protéger l'écosystème marin riche et fragile de notre planète est notre priorité absolue. Le Monaco Energy Boat Challenge illustre parfaitement cette volonté. Le passé est notre patrimoine, le présent notre responsabilité, le futur notre défi.
Our oceans are under serious threat. Yachting stakeholders have the responsibility to mitigate impact and contribute to marine conservation. The Yacht Club de Monaco elaborated a robust benchmarking rating system for yachts based on calculating their initial carbon emissions. This C index offers carbon certification for all yachts over 25 meters, a process independently verified by a maritime class society.
We are very proud of being accepted in this association and to have achieved 3 stars, because that tells us that we are heading in the right direction.
Join us in this crucial endeavor for a more sustainable maritime future. Reach out to us on the C Index website.
Thank you, everyone, and thank you for quickly making your way back to your seats. I would now like to welcome to the stage with their Design Prize, FEUP Academic Solar Team. Thank you.
Hello everyone, my name is Eduardo Estrela and this is my colleague Diogo Leitão. First, we want to start by thanking the organization and the jury for giving us the chance to present our work here. Today we are presenting the FEUP Academic Solar Team project design, the design of a sustainable solar boat. Firstly, just a quick introduction of the team. The FEUP Academic Solar Team project was founded with the objective of bringing naval engineering to our engineering faculty, FEUP. The team now has 48 members that are fully committed to the development and production of sustainable vessels. Our team was founded on the core pillar of sustainability. Our goal is not only to produce competitive vessels, but also to truly innovate in the sustainable field, to hence our motto, towards a greener blue. With this in mind, our first prototype features a hull made 100% of natural fibers, in our case flex fiber, and the boat is powered by renewable energy, and also we ensure that every manufacturing process is as sustainable as possible. But our mission doesn't end here. By proving that sustainable materials and clean energy can provide good high performance, we are demonstrating a viable path forward for the broader maritime industry. We are not just building a boat; we are engineering a greener future. So, just a quick sum up of our boat. Atlantico is a flying solar boat that has an electrical system with a battery with a capacity of 1.5 kilowatt-hour with a set of solar panels that can produce up to 800 watts of power. This system is connected to an electrical motor that can reach a big power output of 10 kilowatts that, when working together with our hydrofoil system, allows the boat to reach up to a max speed of 20 knots. And to just finalize, even though the boat weighs 300 kilograms, it can reach up to 1 hour of sailing when in cruise speed. Approaching the hull design. Being the first vessel designed by the team, we decided to follow the catamaran philosophy with 2 identical hulls. We decided to choose this philosophy due to 3 main benefits. Stability, since the boat was projected to go on open water, so it needs to be stable and withstand the rough conditions. Efficiency, our hull curve is based on a performance hull, and our design was verified via CFD simulations. From these simulations, we concluded that the boat reaches the takeoff speed, allowing the boat to fly over the water. And finally, modularity. This reasoning comes related to the fact that this is our first boat. Hopefully, nothing bad will happen to any of our hulls, but in case that something terrible happens to one of them, we can easily swap the entire hull, or even in the future, we can swap the hull with an improved design without the needing to change the electrical or mechanical systems that are already in the current layout. Just to finalize the hull section. As I mentioned in the beginning, our hull is made of flex fiber. This type of fiber is noticeably weaker than the conventional fibers, such as carbon fiber or glass fiber. And so, in order to reduce the total number of layers used in the hull, structural analyses were done using finite element analysis. From this analysis allowed us to identify the weak points of the boat and to determine the optimum layup sequence. It was then possible to design an internal structure that reinforces the vessel, focusing on the hydrofoils and beams connections. This internal structure is constituted by 6 bulkheads that are made of a biomaterial, which is a sandwich structure between flex fiber and with a core that was fully developed and studied in-house to achieve the best possible configuration.
In order to further increase our boat's competitiveness and efficiency, we wanted to include a hydrofoil system. But also here, we wanted to keep true to our philosophy and values. We used 3 hydrofoils of the T-style that balance our boat much like a tripod. We have linear actuators that automatically adjust the angle of attack of each one to always keep a smooth ride no matter the conditions. Our boat is designed to fly 50 centimeters above the water, which is higher than most vessels of our size. But this is because we truly intend on going for the sea. The design started with a numerical model that was optimized through genetic algorithm, and then iteratively through CFD design, with a big focus on the interaction between the strut and the foil, where a lot of turbulence and drag is generated. With focus in this area alone, we were able to improve the efficiency by over 10%. We were also able to build a hydrofoil system that allows our boat to go at double the speed for the same energy consumption as a normal boat. This allows us to go further and, like our team name says, go fast. But also, like I said, we needed to stay true to our values. And so we decided to innovate and build our forged carbon fiber hydrofoils. This process uses short strands of carbon fiber that would otherwise be waste at the factories. And for the same reason, it is much, much cheaper than traditional carbon fiber cloth. And so we put these fiber strands inside the mold, as you can see here. We wet them out with resin, and then we close and compress the mold to achieve a final part with little to no waste. This process also allows us to use wooden pine molds sourced locally, something that would not be possible with RTM methods. So in the end, we have a part with competitive mechanical properties, weight, and especially at a much reduced cost and environmental impact. This hydrofoil system is mounted to 2 front struts and also to the rear propulsion column. This column has a very tough task. It has to deal with the hydrofoil system, the propulsion, and also the steering. The propulsion comes from an electric brushless motor mounted directly to the column. What this allows us is firstly to mitigate the need for a specific cooling system for the motor, as it is in constant contact with the water. Also, it allows us to use a very thin NACA 12 profile for the column, something that would not be possible if we use the top-mounted motor with a shaft. So not only do we eliminate a system and the source of energy consumption, but we also have a more efficient column. The steering system is based on a typical helm, but it uses a polymeric rack and pinion system designed by us. This allowed us to customize the gearing reduction to have a more direct feel on the steering wheel. Also, with the gears made from PEEK, we guarantee they will never rust and don't need lubrication, and so we have a much longer and maintenance-free life of the system. Quoting Sun Tzu, if you know your enemy and know yourself, you need not fear the result of 100 battles, and that is the exact purpose of our human interface system with this screen you can see on the steering wheel. This system warns us if everything goes right and when everything goes wrong, and also can help us predict when things are about to go wrong. And this is very important, as you know. They tell us information about the battery, the current state of the boat from the inertial navigation system, like pitch, roll, heave, and speed, of course. Also the position of the hydrofoils if needed. We have multiple screens for the different races. But it also allows us to talk back to our boat and define different settings for the hydrofoils, the cooling system, and the solar panels. And yes, we do love our boat, but we also recognize its flaws, and we've already started to address some of them. Firstly, we recognize there is a mismatch between the RPMs at which the electric motor is more efficient and the RPMs at which the propeller is more efficient. Although our first design was made for global system efficiency, optimized for that, we do believe we could do better with this torpedo style. And so since then, we've designed a custom planetary gear reducer so we can sit in the sweet spot of RPMs for both the motor and also the propeller. We also realized that with the pilot being in just one hole, we have uneven weight distribution, and so we have since designed a new set of hydrofoils that has specific area and aspect ratio for each one of the supports. One for the pilot, one for the battery compartment, and also one for the rear column. And also, being such a big hole in the catamaran design, we know maneuverability is not its strong suit, so we have since decided to implement roll-guided curves that use the hydrofoils to tilt the boat inwards and hopefully help us also address this problem. So have we accomplished what we set out to do? We believe so. In just 2 years of conception, our team has designed, built, and competed with its first ever solar boat. We have also tested it in very rough seas, and it even outperformed our expectations. And finally, we provided a platform for all students of FEUP to use for innovation. Members or not of the team, all students can use our boat for innovation, and this will certainly propel the maritime industry. We are not done yet, but we are truly sailing towards a greener blue. Thank you for your attention.
Thank you very much for your presentation. I'll now hand to the jury.
Thank you so much for your presentation. I guess my question for you guys is, you've used flax and cork throughout your production process. What were the challenges that came with those kind of materials?
In terms of manufacturing process, it was actually quite easy because we use that kind of sandwich structures only for the internal structure of the boat, and we've done the structures by infusion. So it's quite a straight up process of just making the structures itself that then are machined to the hulls form, and then they are glued to the hull. But in terms of tests, we tested the structures, especially at the bending, and of course the bending performance it's much higher when we are using a cork core.
And a little question, as we are speaking about environment and impact, did you use a Marine Shift 360 tool to measure the CO2 of your production?
Yes, we did. As presented previously by our colleagues, we have assessed all the environmental impacts of our components, and we do conclude that some of the evolutions we did mitigate the CO2 production of our boat, and we also learned a lot, of course, for future vessels as well.
Okay. And could you also share what was your inspiration to put the driver on the side and not in the center of the design of your boat?
Yes, the main advantage we thought was that this removes the need for an additional structure in the middle and more weight. So by including the driver in just one hole, we hopefully, and we believe so, we have a lighter boat in general.
Thank you. In design, we usually say that form follows function, which is probably here the right presentation to make the connection between this sentence to your project, and the design process behind it is really logic and well applied. But it's very linked to all the engineering, process, manufacturing, hydrodynamics. What is the real link, the human link between your boat to mainly the user? What ergonomically you did to improve the pilot position, steering, everything that he needs to do on the boat?
Yes, so one advantage of having the driver on one hole is it has an advantage and disadvantage. When you're on the right side, it's much easier to get in and out of the boat. Of course, you can't get out to both sides. But also we tested with our pilot, and we tested the position, and then we designed the virtual model of him on our CAD software to position the steering wheel, his feet, and all the supports to the side for him to be comfortable. So we did measure him and did the cockpit to his size. Also the screen, of course, we tried to make it the most visible as well, and chose a screen that would be bright enough for these days, these sunny days.
What, and I have another question. Thank you.
I'm curious about your choice of cork. Did you analyze the real cork content in your decks and in your bulkheads, or do you know the ratio of glue to cork, the granule size, etc.?
So the cork that we use is especially for using in such cores in the composite industry. It is from Amorim, which is the biggest company in Portugal that commercializes cork. And so we followed their advice in what cork to use in the internal structure, giving the final application of the structures itself.
We also tested different cork performances, like thickness and also density, and found the best compromise between both for the flexural strength.
I have naval architecture questions. How did you define the hull separation for the wave making?
Yes, we did CFD design, and we noticed that ideally they would even be more apart, but we had limitations with the class. We wanted to build our boat for the solar class. So yes, there is interference at the very back end of the wave making, we realized that, but unfortunately due to the limitations of the class, we couldn't separate them more.
And the asymmetrical weight, did it have an impact on your choice?
On the choice, no. For those simulations, it was at the very beginning of the team. We didn't even the expertise. And yeah, at first we didn't have the expertise for that. But then we've since developed and we've tested it with already. And yes, we have seen the differences in wave making from both hulls.
Thank you, thank you.
Thank you very much for your presentation.
Thank you.
I would now like to welcome to the stage for our last Eco-Conception Prize of the day, physicist Monaco Energy Boat.
So, hello everyone, my name is Federico Simonazzi and I'm the Business and Logistics Unit Coordinator of Physi FEUP. And today, together with my colleague Sergio Cattuto, the Coordinator of the Dynamic and Control Unit, we will be your guides through our pursuit of a more sustainable approach to racing. So, how sustainable can an unsustainable system be? Probably not enough, but engineering has never been about a perfect world, only better compromises. This year at Physi FEUP, we faced one of the biggest challenges sustainability-wise for our students' team. Trying to extract one clear eco-design insight from our LCA and present it in a way that it's credible, impactful, and accessible. So this required a journey that took us into the depth of all the materials, the processes, the usage, and the end of life of every component in our prototype. All of this while analyzing sustainability KPIs, balancing trade-offs, and evaluating shifts in terms of processes and materials. So this donut chart represents our result. The items are being grouped based on their job. And we can see our result of 6,115 kilograms of CO2 equivalent. But since we don't like easy challenges, we posed ourselves a constraint. During the redesign of a part or a system, we would have accepted no compromises in terms of performance. So from our LCA, we extracted 4 key areas that we could have worked in terms of improvement. The first one is the cockpit mold. The first reason is because it's very heavy. So there's a lot of material, and so a change in terms of material could have produced a big shift in terms of sustainability. The second one is hull restoration, because by repairing our hulls, we can avoid the environmental burden associated with the production of new ones. The third is the usage of bio-based materials. For example, a leather produced with orange industry waste. And the fourth one is shifts in terms of processes and materials in the propeller system. To maintain a coherent line with our constraint and to choose environmental-driven over economic-driven choices, we focused on the most critical component of the catamaran, the propellers. So the story of the propellers of our team began with a single bronze one. Then, thanks to the evolutions of the team capabilities in terms of production and simulation, we got to a dual propeller system, dual counter-rotating propeller system with propeller printed using CPBT, carbon fiber lamination added to the blades to improve their stiffness, and finally, this year, we got to a modular system, building our modular testing platform and improving our efficiency over the sustainability point of view.
Every year, we test up to 22 counter-rotating propeller sets. And having a counter-rotating system, this means 44 propellers, manufactured, tested, and often discarded. So this is a big footprint in terms of CO2 emissions and also in terms of time needed for production, of course. So we asked ourselves, can we keep pushing performance to the limit while reducing drastically the environmental impact? And to answer this question, we looked at our system. So we have 2 counter-rotating propellers, as Federico said, 2 aluminum hubs to transmit the torque, 2 axial locking systems, like the locking ring and the bolt, and a cup to have less turbulence in the wake. So if we now take a closer look to our propeller, these are 3D printed in PC PBTCF, a polymer alloy charged with carbon fiber to increase the stiffness, and then covered with carbon ply to further have a better mechanical strength and good stiffness in the water. So this gives us a great design freedom, good mechanical strength, but the problem is that every new geometry we want to test need a completely new propeller. We have to reprint all the propellers. So that's why we thought to move towards modular propellers. A standard modular propeller is made of an aluminum hub, detachable blades, and an axial locking system, like that one. So these, of course, help us to reduce the material, because we just have to print and produce the blades. But in a system like our, a counter-rotating system, reconfiguring the system is pretty hard and is inconvenient and risky, because we have to dismount all the system. So that's why we thought to redesign modular propellers. Our new modular design have an aluminum hub, detachable blades, a bayonet coupling that help us and give us the opportunity to have an axial and a radial constraint, and spring plungers. These help us in centering and anti-loosening function during reverse operation. So our modular propeller help us to use less material, to have a shorter production time, and are also much faster to reconfigure during testing. So before, to reconfigure the system, we would have needed to dismount all the system. But now with our new modular propellers, the mounting is so easy, and the dismounting is also so easy. So we just need one tool, no expertise, and it's very easy and doable from everyone without expertise. But we know that in engineering, every step forward comes with a compromise. We managed to reduce the variable costs a lot, thanks to the less production time and to the less material. But the fixed cost grow up a little bit. So our cost indifference point sets at 38 about propellers, that for us is about 2 seasons according to our production volumes.
But what's the result of all of this? This is the result we came. I mean, it's a very simple concept. It's like economics. We have shifted our costs because we had lots of variable environmental costs related to the printing of the PCBBT. It is a technopolymer charged with carbon fiber, so it's very polluting. And we have more aluminum right now that is fully recyclable, and over 20 sets of propellers over a year. Considering that we reduced the usage of PCPBT by 48%, we have a reduction from 270 kilograms to 221 of CO2 equivalent. So this is 19% less. But there is a problem. The problem is that even if in the propeller system this shift is quite big, the propellers account for roughly 4.5% over the whole prototype. How did we solve this? We tried to look a little bit further on the time. And we asked ourselves, how else could we leverage the advantages of our modular propeller? Well, producing propellers requires lots of evaluation, lots of validation of your CFD, of your design. And this validation is performed through on-water testing. So on-water testing accounted for 26.85% of our total pollution because we needed to test 20 sets of propellers per year and lots of other stuff. But to reduce this number, we thought that we could have shifted the validation one step before, trying to stay in the university. And how did we do that? In university or at a university partner? Because to reduce the number of testing days required, accelerate development cycles, and amplify the benefits of our modular architecture, we thought about implementing it in hydrodynamic testing facilities so that we can exploit all the advantages by the environmental point of view, all the advantages that Sergio showed when mounting and dismounting the propellers. And also, the objective is not to eliminate real tool testing, but to make every on-water test count more. So imagine having not 20 sets to test, but 4, 5, because you are validated your CFDs. And this is also a modular platform. So we can test propellers of small teams, research labs, just by asking them to scale their propellers or do it in a way that it fits on our hub. That's the only constraint we have. And we can test lots of propellers per day. So thank you.
Thank you very much for your presentation and the round of applause.
Thank you so much for a really clear presentation. I know from your report that you looked at lots of other areas as well, but it's really great that you've able to narrow down on one specific element that you've seen a real progress in. You mentioned that, so when you were developing this modularity and you were looking at how you could develop it, what were the main challenges that you came across while trying to build that?
Yeah, the main challenge have been make them stiff enough. So we came across a lot of design ideas, and then we thought that the bayonet coupling system could have been the solution to our problem. But is not as simple as it can look. So the bayonet coupling, yes, but what are the right dimensions of this bayonet coupling? So we came across a lot of testing, a lot of design. We have done a lot of FEMs to validate it. And when we reached a design that could allow us to have, to have a coefficient, a safety coefficient over 1.5, we said, okay, this could be our design. Of course, there's room to improve it, but this is our design for now, and it seems to be validated.
Perfect, thank you. Does anyone else have a question?
Yeah, it's a bit more hydrodynamic question. You have a contra-rotative propeller, which is okay. We discovered in the past year that that's smarter compared to just having one propeller. But we also discovered that having a towing engine is better compared to having a pushing engine. Could you explain me why you take the decision having this kind of engine and pushing and not towing the boat?
Yeah, this is more related to the motor configuration, not to the propeller. Yeah, of course, we have a pushing motor that is not ideal, but for now, saying that being that the amount of money we have and the sponsor we have, this is the only configuration we can have for now. Of course, we plan to go farther and to go to a more efficient one.
Maybe other question, did you test other materials compared to carbon fiber for the propeller? Because some materials that are sometimes stiffer, sometimes smoother, have some advantages. Have you performed some tests with other materials, or could you explain us why you choose the carbon fiber?
Yeah, Till last year, our propellers were made in PCPBT HF, a blend of polymer charged with little carbon fiber. This year, we choose to have a carbon ply also in it, because we find out that while operating, especially at high power, the blades were flexing. And so a flexing blade push you far from your design geometry. And so that's why we choose this technique. We made a lot of tries to understand how to not compromise the blade shape while producing it, also because a carbon fly can add variables on the geometry. And we found a way that give us the opportunity to maintain the geometry of the blade while having it very, very more stiff.
Thank you very much. Would that be? Sorry.
Just one question. Did you make the comparison between the CFD results and the real life results? So then reducing the amount of blades to produce?
Yeah, the validation of, we have made the validation of our new carbon fiber propellers, and they seems to be they are more near to the operating point that the CFD give to us. So we are still not at that point, but we shifted and we are more near to the operating condition that they are designed for.
Would there be one further question? Thank you very much for your presentation. For our last design presentation of the day, I would like to welcome to the stage again Swiss Solar Boat.
Hi again, everyone. This is the last presentation of the day, so I will try to make it as enjoyable as possible for you. And especially I will try to explain why and how we have been developing our last prototype, the Lobster, for the last 3 years. So to begin with, project framing, at Swiss Solar Boat for like more than 10 years now, we've been building prototypes based on electric propulsion and battery storage. The downside of those technologies, always the autonomy, and also the fact that our prototype was only race-oriented, which means it was limited in terms of finding solution to decarbonize the whole nautical sector. That's why when we try to take a step back and look at the big picture, you can see here the boat from the CGN. And here, for example, there is a tiny graph where you can see the comparison for a crossing between Lausanne and Evian, which are at two sides of the Geneva Lake. If you use a diesel car, that's what you'll see or not see very well on the far left. You have, of course, a high emission impact, and then using the hybrid battery diesel boat from the CGN, you lower the impact. If you integrate a fuel cell, you lower the impact even more. What's the message? The message behind that is that for some routes, both it can be a big impact reduction. Green energies, they have huge potential. But there are, of course, challenges to tackle with renewable energy, as we all know here in this room. This is the philosophy of this boat. We want to build a boat which allows students to experience green energy, is aligned with real-life issues, with real applications, and promotes sustainability through all its life cycle. Well, that being said, we had to research how to do that practically. First of all, we tried to evaluate the different energy vector and storage that were available. Diesel, it's an outstanding energy density, but it's not renewable, so we're not going to use that. And we are left with batteries, solar panels, hydrogen fuel cell. Other exist, of course, but we studied only those three. They have upside and downside, each of them, that we try to wrap up in this spider diagram that you see here. So in blue, it's the diesel scenario. In orange, fuel, battery, electric. in green solar only, and in red H2 fuel cell battery hybrid. We'll try to focus on this red scenario, H2 fuel cell battery hybrid. We can see that the production impact is pretty high, the indexes is pretty low, and that the technical maturity is not high also, but on the other hand, we have low operational emissions, good energy density, and good system efficiency. That's why we decided to go for this trade-off, a hybrid energy system using hydrogen for the main energy carrier, a small high voltage battery as a buffer, and solar panel to feed the low voltage system. That being said, we need to choose a ship type. I don't know why it's scrapped. It's not supposed to be like this, but we went for the foiling system. As everyone knows now, you can see it on the graph. You have the front number on the x-axis, which is more or less the speed of the boat. And when you increase the speed, if you have a traditional Archimedean ship, the drag per unit mass increases exponentially, whereas if you use a foiling technology, it stays reasonable when the speed increases. Sorry. Also concerning the propulsion chain, we decided to go for direct drive. Actually, we have our motor underwater inside our torpedoes, so it's directly connected to our propellers. This means that we minimize the transmission losses, and also that we have direct cooling from the lake or from the sea here in Monaco. Yes, so now we have defined the design, direct drive, hydrofoils, hybrid energy system. What are the goals that we are trying to reach? 1 pilot, 2 passengers, 160 km autonomy, 25 knots, 35 knots top speed. Here the idea is really to get closer and closer from a real-world application. That's what we're aiming at. So first of all, by participating in the MABCC Lab class, and also this boat was designed to try and complete a full loop of the Geneva Lake, as you can see here on the drawing. I will get back to that at the end of the presentation. That being said, we needed a concrete design, how to achieve that, how to do that. Well, those are the first sketches, I think 4 years ago now. Those one became 3D modeling, then even more detailed 3D modeling, 3D rendering, and that's how we achieve the beautiful lobster. In our opinion, she's very beautiful. But that was 3D modeling, right? So how to put that into action? Well, our design philosophy, 20/80 strategy, get 80% of the performance for only 20% of the impact. That means that the use of carbon and other high impact materials, you have to do it wisely, only when it's essential, and take the whole life cycle into account. You know that already. I mentioned it during the eco-conception prize, but from our past LCAs, we understand that the mold, for example, the use of carbon mold was very CO2 intensive. Just to recall, on the left, if you use the full carbon traditional method, and then our method in the middle, you have a reduction of 85% of the CO2 emissions, whereas only plus 15% on the hull weight, which translates in only plus 3% on the total weight of the boat. What I haven't shown in the last presentation is the prototyping, especially of this method. We had to do a prototype of the prototype, actually, because it was the first time we were using this method. So we decided to do a representative meter square of the hull just to gain experience, and we could identify problems and how to address them. I think that Max would be more than happy to talk about this difficult moment. But that allowed us to gain experience. Testing and validation, well, it's a new composite sandwich, so we had to determine the actual modulus and strength, understand the failure mode, optimize the layup. It's a brand new technology, so you have to go through this process. You don't have the regular data sheet that you can use. Many other tests, if we look at hydrogen, for example, we added a module on our last prototype, the DAU, just to gain experience on that. Then our current fuel cell, we could test it twice in Belfort, specialized laboratories. Then once it was integrated, we could test the overall system with Green GT, which are professionals of fuel cells for trucks. We tested our foils, motors test bench. Of course, you have to test all the subsystems outside of the boat before integrating them. And yes, we had to produce this boat. So you've seen those images in the last presentation. A quick recall, but what is interesting in this method is that the wood that you see in the second picture takes the shape of the scaffold because it's stamped on it. Then we can do regular infusion, turn the boat upside down, do infusion on the other side, and at the end we just have a scaffold with particle board that we can throw away in the recycling bin. Many other parts to produce and to integrate. Just to mention here the nose of the torpedo, for example. As I just mentioned, the motors are underwater, so that was also a challenge for the water tightness of the torpedoes. And here comes the evaluation after almost 3 years of design and production and testing of the subsystem, then integration this year of the subsystem into the boat. We could, in February, do a static evaluation just to test the water tightness of the boat. Went well, so that's good news. And then afterward, of course, during the past month, water testing on the lake. To be honest, it's a bit easier on the Lemons Lake than in open sea, but that's how we learn, and it's actually a great playground for us to start testing the boat. To finish with, I was mentioning this was really designed to try also to complete this loop of the Geneva Lake, 160 kilometer. We are actually trying to create this with the Société Nautique de Genève. They have other ribbon, they have a blue ribbon, for example. This one would be only for boats that have no emission during sailing. Yes, you get a score at the end that is not only based on the time you made, but also on the efficiency of your boat. So competition open to everyone. That's why also we're trying to create. To finish with, you know how students are. We always want to go further with these 160 kilometers. We can dream of open sea crossing. If we could complete that, not next year, but maybe in 2 or 3 years, we'll be very happy, maybe from Monaco to Corsica, I don't know, because that would showcase the fact that we're getting closer and closer to real-world application. Those are, as I was mentioning, what we're aiming at. That was Swiss Boat. Thanks for your listening.
Thank you very much for your presentation. I now welcome some questions from the jury.
Thank you for this second fantastic presentation. You made the boat larger for more people on board.
Yes.
What are the accommodations looking like on board? And if you are using the full autonomy, I believe that you will need something at some point.
Yes, so it's still a prototype and a student boat, so the accommodations are a bit rough, I would say. The cockpit, I don't like to say but I worked a lot on it, so I tried to make it the more ergonomic for the passengers and the pilot. So it's more on the ergonomic side rather than just accessibility and having other commodities. So you have a full dashboard that is really ergonomic and aesthetic to be able to handle whatever you want. You have a bench to sit everywhere, and you can walk around the cockpit easily. But behind we have the fuel cell, and in front of we have the battery and the hydrogen tank, so we don't have that much space. So not really other commodities than just the cockpit, sorry.
That's a good way of improvement to get closer to real-world application, indeed.
So first, yes, you will do the crossing from Monaco.
Thanks a lot.
And the second question, could you please explain a bit the trade-off you choose in between stable flight and efficiency? Because that's a difficult question, because it's easy to take off with a wider foil and easy to control the flight stability. And you need that when you go in a rough water, but then you lose on efficiency. So I am personally interested, for example, if I would buy a boat that it's a foiling boat that cross the ocean, I want to know with this foil, what is my potential stability. So I need to understand this crossover in between efficiency and stability.
The main innovation we made, can you please show a picture of the lobster, please? Yes. So we like to do some stuff that are not that easy. So the boat is hard to stabilize, as we saw in the rough waves, but we're working on it. But the main innovation is that the whole gantry is actuated on this side, which can put angle of attack on the whole mainfoil, which leads to a shorter span of the foil. So the foil is actually way smaller than it should be if this was not actuated. So we have really small foils that induce way less drag. I would not have the comparison to another bigger foil, but we know this was a key point to, sorry, I'm lost. But yes, so this is one big innovation. So you have a really shorter foil and so less drag, but it's, as you can imagine, harder to control. But the flaps here help us to control the boat. And in Lake Geneva, we can have some pretty stable flying. This morning, when refueling, we made stable flying, but with that much sea, it's hard to foil. I would say that with motorized boats, foiling boats, it is hard to have a stable flight with that much waves. Maybe if you have another kind of force, which is not only flying and more helping the boat to reduce its own drag, as you can see the ferries in Italy, sorry. This would be interesting, but for a full flying boat, I would not recommend, for the moment, going to rough seas.
And after, could you please explain a bit more on the design philosophy? You explained that that was a 4-year study from the first sketch to this boat. So could you please share a bit the inspiration that gives this final design?
So at first, the choice was to choose between a monohull, a catamaran or trimaran. And so basically, I should not say that like this, but what was chosen is the hybrid one because it looks beautiful. No, it was at first this, but we saw after, this was to be honest, but after, as you know, a foiling boat can have the critical crash nosedive one, as we can see in America's Cup all the time, and as we did yesterday. But the floats on the sides here are used as crash box, and they're supposed to take the loads of the impacts of nosediving. So it was at first beautiful, and now it's really useful for us. So this was the main choice at the beginning, and after iterating, we really wanted to have this race style design.
99% of the time, we try to make it first useful and then beautiful, but sometimes it's the other way around.
Now, just a quick comment.
Yes.
The shortest distance between Monaco and Corsica is Monaco-Calvi.
Yes.
It's
Yes.
106 nautical miles. So please extend a little bit, and you will do it. You will have all our support.
Okay,
Thank you
challenge
very much,
accepted.
Will.
Thanks.
Thank you very much for your presentation.
Thank you.
Sorry. I would like to conclude our session by thanking the audience. Sorry. I would like to conclude this session by thanking the audience who have endured the slight lack of AC, and I apologize, and really put an effort into welcoming and congratulating our participants, which is much appreciated. I would like to also invite you all to the eSport Championship later on in the meeting room. I believe it's at 7. And good luck for all teams that managed to qualify for the championship. And thank you again for being here today. So I will close the session by trying to ring the bell with a bit more force than yesterday.